Hello everyone, welcome to Computational Foundations of GIS, our module in the first semester of the International Master's Program Geodetic Engineering at the University of Bonn. My name is Jan-Henrik Kaunert. I'm professor for geoinformation here at the university, and I will teach also several elective modules during your master's studies, especially those of you who are in the profile geoinformation and spatial development will hear more about geoinformation systems from my side. But this module here is compulsory for all of you, and it gives the general basics of geographic information systems, and particular their computational foundations. I have here a set of slides to cover two lectures. Well, I will make a break at half time so that this will be split up into two videos. The first one here given the general overview of geographic information systems and some basic concepts. Well, geoinformation systems, or in short GIS, sometimes also called geographic information systems, they are systems providing tools for the acquisition, administration, analysis, and visualization of spatial information. And this acquisition is done with different sensors from different platforms. For example, there's a close link between geographic information science and remote sensing, because a lot of our information is collected with remote sensing satellites. On the other hand, we have also terrestrial sensors, such as a terrestrial laser scanner, which you can see here. Then, once we have captured the data, we need to administrate that data. Of course, we need to define appropriate data models and data structures to keep the data in our computer systems and to ensure that the data can be accessed efficiently. Then it's important to make use of this data, of course. We need to analyze that. So for this we need algorithms dealing with the data, for example, data mining algorithms. This one here is an example showing where, well, roofs of buildings are classified according to how much they are suited for solar panels. So you can see here in red, those are the buildings which are very promising for solar panels to to be placed on the roofs and in order to collect or to produce energy. A second example, this is visibility analysis. So suppose you are standing somewhere here on this hill. In red you can see all the region which is visible from that location. And in addition to analyzing spatial information, it is also important to visualize it so that humans can actually get an overview of the data and make some use of it. This relates, for example, to three-dimensional visualizations in terms of these virtual city models, but also it relates to interactive maps, for example, maps for mobile devices. Smartphones are quite common nowadays as tools to display maps. And especially in the second semester of your studies, there is the module location-based services, where we will deal with, well, cartography on small devices, for example, which is shown here as an example. So here you can see a certain labeling model where points of interest in this map are labeled with these text labels. So cartographic label placement, that's a problem we are working on in my working group here at the University of Bonn. Well, there are several components of geoinformation systems: hardware comprising sensors and computers, software comprising programs, and you can also count data as software. Well, some people also say that humans are an important component of geographic information systems, like the users, the experts themselves, they are also a component of a GIS. And then there are GIS programs or GIS software, computer programs like ArcGIS, which is, I would say, the leader in the commercial sector. And on the other hand, there is a lot of free and open source software like QGIS, which we are going to use also in the exercise. So this is becoming larger and larger, I should say, that this free and open source software, it started, well, with an active community, enthusiasts who wanted to develop their own software to be used by everyone. And nowadays even, well, public offices and companies use this free and open source software quite a lot. As an example, this is QGIS, and well, if you open ArcGIS, for example, it looks quite similar. Basically, you see that the whole project here is organized into several layers. So you have different layers of information. The first one here is a road layer, the second one is a building layer, and the third one here is a satellite image. And that you can see then in the map. Yeah, so you have, here you have an overview of the layers that are loaded in your project. And then you have here a map view where these layers are displayed geometrically. And then, of course, you have a lot of toolbars to allow you to compute something and, well, to make some analysis in particular. If we are talking of data, then in general, we need to distinguish vector data and raster data. So vector data comprises points, lines, areas. Raster data, however, means we have a grid of raster cells, so it's discretized into pixels, picture elements. And in addition to these vector geometries, points, lines, and areas, we usually have attributes, non-geometric attributes. Well, here this example is not very good, I need to say it. It's just an object ID, the length of the shape, and the area of the shape. But you can think of more thematic attributes as well. For example, describing the number of floors of a building or the category of a road, yeah, whether the road is a highway or a residential street, something like that. Can all be recorded here in this attribute table. So you see columns represent attributes, rows represent features consisting of consisting of a geometry and its attributes. Well, so that was just to show how such a geographic information system program looks like. And let's talk a little bit more about raster and vector data. So, as I said already, raster means it's basically a matrix with raster elements. And vector means it's consisting of points, lines, and areas. And you know raster data, especially if you take photos with a digital camera, for example. So then you usually have 3 channels, namely a red, green, and a blue channel. That is because the human eye has 3 different sensors which are sensitive for red, green, and blue color. And therefore our cameras also use these different colors. So that is useful for us as humans because those are the colors that we can distinguish. And well, we have these three channels, red, green, blue. Then for each pixel, meaning each picture element, we basically store three numbers. And the mixture of these three values is then perceived by us as humans as color. Well, if you think of these standard consumer cameras, usually we have for each channel 8 bits. So that implies we have 2 to the 8 different values. Yeah, so it means we have 256 different values of green that we can display. And similarly, 256 values of red and 256 different values of blue. And in total, that means we have something like 16 million different colors we can display with this 8-bit color model, so 8-bit for each channel. Something you should know, of course, is well, how do these binary numbers work? So 8-bit, that means we have an 8-digit binary number, something like this. And binary number means, well, if you want to convert that into a decimal number, this one has like value 1, this has value 2. This one would have value 4, but because there's a 0, there's nothing. This one would be of value 8. This one would be of value 16. But because we have a 0, that's simply nothing here. And then we would have, for this one, value 32. So in total, this one would be equal to 43 as a decimal number. Yeah, and you see, we can count like this. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. So that's how to count with binary numbers. And if we have 8 bits, well, of course, with every bit, we increase the number of binary numbers that we can display by a factor of 2. So therefore, with 8-bit, we have 2 to the power of 8 different binary numbers that we can display. Okay, let's switch back to my slides. I should say that raster data is not only used for photos, especially in geographic information systems. You may think of raster data, for example, representing different classes of land cover or different classes of land use. So here in this example, let's say we have a matrix, and every matrix cell contains only a single number. For example, this code here, 4107, that would be contained as a number in this raster matrix, and that is the code in the German topographic database representing forest. So you don't have this 3-channel digital image, but on the other hand, you still have a matrix, every raster cell now contains somehow a code representing some land cover class. And, well, of course, if you show this in a geographic information system, then this code is somehow translated into a color. But that needs to be defined. So you, as a user, usually need to say, okay, let's say 4107 is displayed in green. So then you convert this raster data set into an image with these 3 channels RGB. Yes, so you simply say code 4107 should be displayed with these colors, namely red equal to 0, green equal to 255, blue equal to 0, so you get a full green for forest. But originally in this matrix you have only these values which are codes for land cover classes. Well, so much about raster data, and let's talk about vector data next. I said already that's points, lines and areas, but actually if we look at some international standard, ISO 19125, that defines the different geometry types for geographic information. And in general, vector data means that the geometry is represented with coordinates. For example, a point consists of an x-coordinate and a y-coordinate. And now we are not restricted to some raster, but that could be any point represented with a pair of real numbers, for example. Well, and similarly, a line string, for example, would be a sequence of points, each of which consists of 2 coordinates, namely x and y. So these are kind of basic types. We have a polygon here. Polygons may have holes. We have line strings. Line strings are concatenations of multiple of these line segments, which are called line according to this standard. Then we have a linear ring, which is kind of a special line string, namely one that closes as a loop. And then we have these single points. These are the basic geometry types defined in this GIS standard. Well, then we have basically a class hierarchy here represented with these arrows. So you can see that, well, a line is somehow a special kind of line string. It's a specialization of line string, because a line is just the special line string which has only 2 points or 2 vertices. And on the other hand, a linear ring is a special type of line string, namely one that is closed, where the first and the last point are the same. And what we can also say is that a line string is a special kind of curve. And, well, this curve class here is now defined in an abstract way to generalize several different concepts of curves. Well, you see line strings, linear rings, and lines, of course, they are all specializations of this type curve. But you can also introduce maybe your own class that is a specialization of curve. For example, you can define circular arcs. Now, that is not defined in this standard, a circular arc. But this standard defines this abstract class curve. And if you need a circular arc, you need to define your own class and say that it's a specialization of type curve. Well, and similarly for polygons, there is this abstract, more general class surface. And there you may think of maybe you need a class to represent disks. So a disk is a filled surface, a filled circle. And you may also introduce a class disk, which is not part of the standard, but you can say that this disk is some specialization of this class surface, which is part of the standard. And thereby you define your own class and its relationship to the classes in the standard, because you relate it to the class surface by saying that the disk is some special kind of surface. So you can read these arrows like a polygon is a specialization of a surface. You can also read these arrows in the reverse direction, saying a surface is a generalization of a polygon. Well, this is what I just explained with circular arcs and maybe surfaces or circles and disks. I should say that this standard also defines more geometries, namely so-called multi-part geometries. If you think, for example, of New Zealand, well, it consists of these 3 islands. Well, there are, of course, many more very small islands, but let's say New Zealand mainly consists of these 3 islands. And to say that this altogether is one object, we need this concept of a multi-polygon. So a multi-polygon consists of multiple single polygons. Similarly, we may have a multi-point, which is a collection of multiple points. And we may have a multi-line string, which is called a collection of multiple line strings. So, and then you see that there are also these concepts like multi-surface, which are collections of surfaces, and multi-curves, which are collections of multiple curves. And finally, we have this most general type, which is geometry collection. So that means that, well, this can be a collection of anything. It can contain, at the same time, points, polygons, and line strings. Just as an example, well, I was once traveling in Sweden, in North Europe. So Sweden somehow looks like, I'm trying to show how Sweden looks. Well, this is maybe like this. That is Sweden. So it's stretched quite far from south to north. And then you have many lakes. In Sweden you have many lakes. So now if you would like to represent the land of Sweden, that will be a polygon with holes. Yeah, so now the polygon contains just this one here. And these lakes, they may represent, or they may be represented as holes. And then, of course, Sweden also contains islands, like this. So now we have not just a single polygon, but if you want to represent everything as one object, you need one multi-polygon. And most interestingly, these lakes are quite big, so in these lakes you also have more islands. Huh? So now you would have a multi-polygon consisting of 1, 2, 3, 4 single polygons, and this first polygon has 2 holes. So that is possible. And you can think also of maybe this island here containing a lake again. So here this is water. So again you have 4 polygons. The large one here has 2 holes, and this small one here, which looks like a donut, that has 1 hole. And altogether that can be represented as one geometry, namely a multi-polygon where 2 of these polygons contain holes. Okay, so if we show this all on one slide, you can see here these different geometry types which are defined in the standard. And then there's one more type, namely the type geometry in general. So that just says that everything is a geometry, no matter whether you have a polygon or a multi-polygon or a line string, everything, all of these geometry classes are geometries. And this concept is, well, kind of useful because some concepts, they can be defined for geometries in general. For example, no matter which geometry or which type of geometry you have, you can compute a centroid for a geometry, yeah? The center of gravity. Or you can compute a bounding box, yeah? A minimum and closing rectangle that you can compute for any type of geometry. And these properties shared by every type of geometry, they are defined in this class here, geometry. Okay, well, to look at some examples, most often geographic data is stored in binary format, which is not easily readable for us. But there is, of course, well, or there are multiple text formats where you can actually open the data in a text editor. And, well, one example is this WKT format, or well-known text format. Another example would be GML, Geographic Markup Language, that is also a text format. And this kind of vector data file can be opened in any text editor. Well, and for example, points can be represented as this string. Now you have, first of all, the string point, clarifying that what comes now is a point object with x coordinate 30 and y coordinate 10. You can also have something with decimal numbers, maybe 30.5 and 10.2. Of course, that's also possible. And here you can see the example. So that is a point here. Well, these grid cells which are shown here, they have size of 10 times 10 units. Yeah, that's a point. And then we have a line string. A line string is a sequence of points. So you have these round brackets, and then you have pairs of coordinates separated by comma. So the first pair here represents the first point of the line string, then you have the second point of the line string, and finally the third point of the line string as it's shown here. Then we have polygon, and there it's required, first of all, that, well, similarly to line strings, we have the sequence, first point, second point, and so on. And then the standard says that at the end you should repeat the first vertex. Well, just to make sure that the whole polygon closes. You can see here that other than in this line string example, here we have one bracket opening and here it's closing. For the polygon we have two round brackets which are opening here and closing here. And, well, what does it actually mean, or why is this needed? That is because the first bracket here, that is kind of opening the polygon, and the second bracket from here to here, that is representing the outer ring of the polygon. Yeah, so the outer ring here in this example consists of 4 points or 4 vertices. And then this second round bracket here, that represents then the inner ring, namely the whole of the polygon. And because this polygon here, that has no holes, and therefore you have two brackets opening here and closing here. So it contains only this outer ring defining the outer boundary of the polygon. But if you have polygons with holes, then each hole is represented with such a sequence in round brackets. You can see also that in this well-known text format, you can see here that we start at point 3010, then the next point is 4040, then 2040, then 1020, and then back 3010. So for this outer ring, we walk around the polygon in counterclockwise order. However, that's different here for the inner ring, for this hole. There you can see we start here in that point, and then we have next 3535 and 3020. So here we walk around this ring in clockwise order. And as a general rule, you can say that these rings are always oriented such that on the left side, if you walk around this string, you find the interior of the polygon. Yeah, so that is true for both this outer ring. So if we walk here in counterclockwise direction, then to the left we always find the interior of the polygon, which is displayed here with this blue. And similarly for this hole, if we walk now in clockwise direction, again to the left side we find the blue polygon. So those were basics about raster and vector data. And now there's also, well, a slightly different classification of data, and that relates to object-based data and field-based data. It is kind of similar to this raster versus vector topic, but it's not the same as we will see here. So this field-based and object-based, I would say, view that is more like the philosophy that you use to model the reality, the philosophy, or maybe, well, the conceptual idea of how to see the world. And first of all, what I need to say, of course, we are not only interested in the geometry of objects, but also in these non-spatial attributes. For example, what does this polygon mean, or this data set mean? Which semantics does it have? And you can think of maybe a land use data set where every polygon is assigned to some land use class, farmland, grassland, settlement, for example. So, and now let's talk about this field-based philosophy and this object-based philosophy. And, or rather, these are two different approaches to modeling the real world. Yeah, so if I look outside of the window, what do I see? And how do I describe it? And there are two fundamentally different approaches. The first one is I consider the world as somehow a field. Well, that is basically a function. So a function f, and this function defines for every point in space some value. Here we can think maybe of a two-dimensional space r squared, so that is our plane, and every point in this plane is mapped to some value. You may also think of a three-dimensional space, and maybe this is every point in this three-dimensional space is mapped to multiple values. But to keep it simple, let's think of a two-dimensional space and every point being mapped to some value. That can be, for example, well, this term field, you may think, for example, of the gravity field of the Earth. Yeah, there you have, in every point of space, you have, well, the gravity vector pointing downwards with a certain magnitude. And these values describing this vector, you can basically find in every point of your space. In every point of your three-dimensional space, you find the values of that vector. So that is gravity field, for example, as an example from geodesy, or let's say from physics. But this concept can be generalized to any function. We may also think of, well, we have the plane, and for every point in the plane we have some height value of maybe our topography. So that is also a field. Yeah? For every point in the plane we have a corresponding height value. Or we can also think of the plane, and for every point in the plane we have somehow a land use type. That is conceptually meaning we have our information represented as a function, as a mapping between space and value. And you can see here already that it's quite natural, of course, to use a raster representation for such a field. So conceptually we have a function defining a value in every point of our space, and using a raster representation we simply discretize the space and we store one value for every raster cell. However, we may also think of a partition of the plane into polygons, each of which has a unique, or each of which has a single value. For example, land use type. Yeah, so again, we have, for every point in the plane, we have precisely one land use type. So we have a complete coverage of the plane with polygons. These polygons do not overlap each other. We don't have gaps between these polygons, because then this function would be undefined. But all polygons together, they basically represent this function, namely the land use type for every point in the plane. And although we have this vector representation here, which contains polygons, this is actually reflecting this field-based view. The plane, that is kind of our space, and for every point in that space we have an assigned value. And these polygons simply represent this function. So, and then there is this different concept, namely it's the object-based view. I don't start with the space and I would like now to define a value in every point of our space, but rather what I do, if I look out of the window, I start to separate objects from each other. I see, okay, outside there's a building and a road and a second building and so on. And these entities, these real-world entities, that is what I'm modeling. So I'm starting to model this building here, maybe as a polygon, and I'm representing this real estate boundary with a line string or something like that. So here we have these objects. These objects have their attributes. A building may have its height or the number of floors, and the road may have a type like the road category, highway, or bicycle lane, or something like that. So let's think more about this field-based approach. I gave you an example already, the gravity field, but that could also be the magnet field in physics. And it can also be applied, the same idea, for all kinds of geographical phenomena, like the height of a surface or the land cover type, as I mentioned already. And in mathematical terms, it can be a function, as I showed on the previous slide, mapping for every point or every point in the plane to a real valued number. But it can also say that, well, maybe for every point in the plane, we have an integer number representing somehow a category. And this kind of function here, that has a name, that is a discrete value field, or also it's often called categorical coverage. So we have categories represented with these discrete numbers maybe. And, well, that is our function f. And on the other hand, this one here, which is probably more natural, like the magnet field, gravity field, those are usually these continuous value fields where we have these real values. How to represent these fields? I already said it's quite natural to do this with raster data. However, you can also use polygons, a planar partition, meaning a partition of the plane into polygons that are not overlapping each other. So, well, actually the term partition already implies that these objects are not overlapping each other. And according to this field idea, these polygons must not overlap, they must not have gaps. Also, according to this field idea, it is not reasonable to have a boundary separating two polygons of the same category. Because, well, our polygons are just there to represent this function. They have no other meaning. And according to that, well, such a boundary here would not be meaningful. It can be useful, however, because if you don't introduce such a boundary, you may have huge and complicated polygons. Think of a river like this one here. Of course, it can be very long, like the river Rhine in Bonn. And if you would like to represent the whole surface of that river, somewhere in Switzerland, it has its source. So the Rhine has its source in Switzerland and its mouth in the Netherlands. And if you would represent this object as only one single polygon, of course, then you run into troubles because that kind of shape is difficult to handle. But that would be the only reason why we would introduce maybe these cuts between polygons of the same category. According to this idea of the field, the only thing we are interested in is modeling that function, and there we would basically model everything which has water and is connected. That is one polygon then. So there's more about fields. We can represent fields also with a collection of data points. Let's say we have these n data points to represent a surface, maybe the surface of the topography. And for every point P, we are given this value of the function of the height of the surface, for example. Yeah, so that is our input. We have these points, this discrete set of points together with values at those points. And then we can say that, well, to define the whole function for our complete space, the whole plane, not only these endpoints, but we would like to have the function in all points of the plane, then we introduce somehow an interpolation rule. And together, this point set, the function values at those points, and the interpolation rule, that defines this surface. And that is, of course, a good representation for fields. So as an example of such an interpolation rule, we can use triangulations. They define a, well, they give a piecewise linear representation of the surface, because every triangle is a plane which can be tilted slightly, so there's some non-zero slope. And this triangulation then says that within this triangle we assume a linear property of our surface, and that allows you to interpolate the value here at this red point, although these data values are given only at these black points. And that is one way to represent this field, which is of course different than using a raster representation. Now, you will see that actually we are much more often working with object representations. I should say that this is also the focus of my group. If you look here at the Institute, you have a remote sensing group chaired by Rebana Rocha. You have a photogrammetry group chaired by Cyril Stachnes. These two groups, they focus on images, image analysis, and these things. So they are quite commonly working with raster data. Whereas what we do in this geoinformation group at the University of Bonn, it relates a lot to geometry, processing, and object-based modeling. So we deal a lot with vector data and object-based models. And therefore, this will also be the focus here of my presentation, because, well, raster analysis, that is also closely related to image analysis, and that will be taught in other lectures. And according to this object-based approach, we say that, first of all, every object is somehow an autonomous unit, and this is somehow separable from other objects. So we can say this is a building, and next to it is another building. And we can draw the line and say, okay, these two objects, they are separated from each other. An object consists of non-geometrical attributes and its geometry. So let's think of a building. We may model a building with a polygon representing the footprint of the building. We may introduce an integer number to represent the number of floors of the building. The building may also have a road number, a house number, maybe also an address or something like that. A street, on the other hand, well, that relates to the scale and the level of detail that we use. Of course, for some applications, it's also useful and reasonable to represent a street with a polygon. However, if you think of navigation applications, for example, navigation systems, there it's more useful to represent streets with line strings. For example, with the center line of a street. But then we have maybe some numerical attributes like the number of lanes of the street and the maximally allowed speed on that street. All this is relevant for navigation systems, for example. And that I should also point out that, of course, which attributes should we collect? Well, that heavily depends, of course, on the application. It's a completely different application to use a road network data set for a navigation application than to use it maybe for a cadaster. We say also that every object is a member of a class. So we can always say if we have an object, maybe that's a building or that is a street. And that is the object-based approach. These three terms are extremely important: classes, objects, attributes. We should not confuse these terms. And you can think of these three terms according to the following metaphor. Let's think of you have a paper-based information system. So we are not talking of computers anymore. Let's think of this analog paper-based system. Then you have, for example, in this paper-based system, you collect information about students maybe, and for every student you collect certain data, for example, the year of birth, the name, maybe you also get a student identifier. That is the information that we collect. And basically the class, that is the form to be filled in. Yeah, you have this sheet of paper, the form, where you need to give your information. And this form, without the given information or without the information having been inserted already, that is the class. So this form, that is the same for all of you. For every student, it's the same form. So for all objects of the same class, it's the same form. And then the object, that is one instance of the form with the given information. So for you in particular, you as one student, you would have this form. It would be filled in with your name, your identifier, and your year of birth. And that is then the object, this form filled in with information for one entity. And finally, we have attributes. And this is just one field of the form. For example, the field for name. So we have the attribute, that is actually part of the class, and then we have the attribute value, that is your personal value for that attribute. So your name, Smith or Miller or something, or your personal name, that is the value for that attribute. Well, these were really important terms. And next, I'm talking more of the process of data modeling. So now that we have clarified what is a class and what are its attributes, now I'm going to talk about, well, if you have some problem, some application, how do you develop a data model for it? Which classes to introduce and how to specify them, basically. Okay, and first of all, we have, of course, these real-world entities. That is what we see when we look out of the window. These real-world entities we model as objects, for example, polygons with attributes. And this always means that we capture only parts of the reality. We never try to model all aspects that we can find. It's never the task to go out and say, okay, I want the reality as detailed as possible with all aspects and properties. I want to put this into the computer. That is usually not the task, but it's always the task to abstract the reality using a model that reflects certain aspects of the reality for a given purpose, for some application. For example, for navigation or for urban planning or something like that. So it's always a specific purpose that we need, otherwise it doesn't make sense to start modeling. Maybe we need our institute building here in 3 dimensions, but with very low detail. So it's just this 3-dimensional box. And we see the real world entity here, and correspondingly we would have a very coarse 3-dimensional vector representation of that building. And that has attributes, maybe name, address, number of floors. Think maybe of applications like facility management. Yeah, so of course the company who is cleaning this building needs to know how many floors are there, what is the size or the area of the surface that we need to clean. So attributes like this might be relevant then for the facility management. Then we have this modeling procedure, and a nice picture is this one, where you can see that this modeling is usually done in several steps, from very coarse to very fine. Or no, actually not from coarse to fine. I should rather say it's from rather conceptual to more concrete. That is actually the sequence. So we are there starting with rather conceptual modeling and then going to very concrete implementation of the model. So that is this modeling procedure, which we need to solve quite often as geographic information scientists, or let's say geodesists. Well, the first thing here, the user requirements, or let's say the requirements coming from the application. I already mentioned the example facility management. There's this company responsible for cleaning the buildings. And we would usually start maybe as engineers, or let's say we would like to develop an information system for that company. Of course, we would start with interviews. We would ask these people, what do you need? Which kind of data, which aspects of the building do you need? And that is basically collecting the user requirements. And second, we have to model now our system in terms of classes, attributes, and the associations between the classes. So how do these classes relate to each other? Maybe you have a room, and that relates to a building, because a room is part of a building, and things like that are modeled as associations. The next step, that is now the logical model. That is about now implementing this, for example, in terms of a computer program, or let's say a concrete database. And there we usually need to decide, for example, how to structure the data, which data types to use, like int or double, float, string, character. So those are the data types that are used in certain programming languages or in certain database systems. So there we need to concretely decide for which data type to use. And well, here we have already attributes, like the height of the building is one attribute. And we can say that conceptually that is a real number. A real number is a mathematical concept. Yeah? A real number has arbitrary precision. It has not a limited number of digits, for example. But when we go then to the logical model, we actually decide I would like to represent this real number as a double precision floating point number, meaning a data type double is used then. And this now has some limited precision, and it is well defined according to our programming language or database system. It defines that data type. So conceptual modeling is more like considering the conceptual and mathematical aspects, and logical model is now to decide which data types to use concretely. And finally, we have the physical model that relates now really to how this model is stored and organized, maybe on the hard disk of my computer or of my server, or maybe it's on a CD, in a compact disk. So how it is really physically stored. And it is rather rare that we go down to that level. So that is usually taken care of, let's say, by the database management system. So it's rather uncommon that I bother about these issues. So it is more common that as geographic information scientists, we go through these first 3 steps: collecting the user requirements, developing a conceptual model, and then implementing that as a logical model. So I have one example here, a running example, I should say, which I will show now in the following, well, in quite a lot of details. And this is an application which I found online. There is this pizza delivery service. Well, they have the name Da Luigi. My Italian is not really good, so please forgive me about my Italian pronunciation, but this pizza delivery service Da Luigi, they are operating here in Schwabach, which is a German town, and the surroundings of that town. And this pizza delivery service, they need a database to administer their customers, orders, deliveries, meals, and to keep that information, like which customer ordered which meal, what is the price of that meal, what are the items the meal consists of. That should be collected in a database. And, well, this pizza delivery service, they invented kind of a complicated pricing system. This is not made up by myself. It is really like this there. So they have different zones, and depending on the zone where you live, you need to pay something extra for the delivery, for example. So if you live here in Schwabach, then you have this minimum order value of 10 euros. So at least you need to order for 10 euros. Otherwise, they won't deliver. And they charge you a delivery cost of 3 euros. But that is still the best you can have, actually. Living in zone 1 is really nice because you will have nice pizzas every day, maybe. But if you live in zone 2, it's getting more expensive. So here you have this minimum order value of 30 euro and a delivery cost already of 5 euro. And finally, we have zone 3. Well, only if you are hosting a big party maybe and you really order for 50 euro, or maybe you order some fancy wine which is very expensive, then they will deliver that to your address. And they also charge you a delivery cost of 5 euro. And then finally, everything that is displayed here in gray, we can call that maybe zone 4. And if you live in this zone 4, then there is no fixed rule. You simply need to call and negotiate with them. Only after consultation by phone, you will get the price and the information actually whether your order will be delivered. That is the rule, or the set of rules. And, well, I now want to start already. Let's say we are having a nice discussion with these people, we know what they want, and now we come here to this first draft of the conceptual model. What I'm using here for conceptual modeling is UML. UML is the Unified Modeling Language, which is a set of diagrams that allow you to model these conceptual models. So I'm using in particular the UML class diagrams. And that is shown here. It's an object-based conceptual model with these 4 different classes. The first thing that you saw also here on this slide, of course, we somehow need to represent these zones, right? That is of central importance. So we have a class zone. In UML diagrams, every class is represented with this box, and this box consists of multiple smaller boxes, and here in this topmost box, or in this first row, there you see the class name. So it's the class with name zone here. And below that box you will find these attributes. Let's say we have the ID of a zone, zone 1, 2, and 3, those are the IDs of this zone. Then we have the min amount, that is like the minimum amount you need to order so that your order will be delivered. So it's actually here this minimum order value, 10 euros, 30 euros, 50 euros, depending on the zone. And then we have delivery cost, which is, well, this 355 euros. And for all these 3 attributes, we say that should be represented as a natural number. In UML, that is defined as unlimited natural, so it can be a natural number which can be arbitrarily large. Of course, that is not the case if we implement that in a computer. Then we always have limited precision and limited sized numbers. But conceptually, we can think of these as unlimited natural numbers. So that is the mathematical concept. I'm saying here that these euro amounts, like this min amount and the delivery cost, that is a natural number because you can think of cent values as integers. Yeah, so 3 euros would be represented maybe as 300 cent or 300 cents. That is the first class, and then of course for us as a company, maybe the most important object is our customer. Of course we take our customers really important, and they have a very central position therefore here in our conceptual model. So the customers will be maintained in our database as well. Well, we have the class name, customer. We have, for every customer, we have a customer identifier, meaning this ID. It's again an unlimited natural number. We have attribute first name and last name, which are of type string. We have attribute address, maybe the street name where the customer is living, also as a string. We have the postcode, the postal code of the customer, and the house number. Those are integer numbers, so unlimited natural numbers. Integer numbers would also be a negative number, but house numbers and postal codes, of course, are only positive numbers, so therefore it's unlimited natural here. Then what we also have, like the menu items, you can think of these menu items, that is actually one item on your menu, or let's say on the menu of this pizza delivery service. So they have an ID. Yeah, I would like to order number 13 from the menu. So every menu item has a number. That is this identifier. Then of course we have, for each menu item, we have a name. Let's say pizza fungi or pizza margarita. Yeah, that is the name of this menu item. And then we have the price. Here again we use cent values as natural numbers. Maybe it's 1,300 cents, meaning 13 euros for a pizza fungi. And the menu then consists, of course, of all these menu items. We could also model the menu as one class here, but I did not do that because I think there's only this one object of class menu, and therefore I skipped that class. So let's say we are just talking of these menu items. But of course there can be multiple different menu items. Then we have the order. Yeah? One customer calling us and ordering something. And this order we also keep as an object in our model so that we can keep track of orders. Yeah, we can see then later which customer made which order. And for each order we can also see what was ordered, which menu items were ordered. And here we simply say this order has just some identifier, so every order has a unique ID, like 13472 or something like that. That is one order, so that we can distinguish the different orders among each other. So these are the four classes we model. We also have now also associations between these classes. And these are represented with these black lines. Because without bringing these different classes into relation with each other, actually we don't have much information here. It is important for us, like who made an order and which menu items were ordered. So therefore we need these links or associations between these different classes. First of all, for the customer, we store the zone he or she is living in. And that you can see here, we have this association between customer and zone. And this text here with this black arrow, that gives you information about how to read this association. So we can see that customer lives in zone. That's how to read this association. Every customer lives in a zone. And actually, what you can see here, these numbers, those are called multiplicities. And they tell us like how many customers live in how many zones, something like that. And to say this more precisely, what we can see here is that every customer lives in 0 or 1 zone. So that is because we only have these 3 zones defined, 1, 2, and 3, and maybe some customer lives outside of these zones. Nevertheless, because he made a big order, he was still served by our company, therefore he is still a customer, but not living in any of these 3 zones. So every customer lives in 0 or 1 zone. That is how to read this. And we can also read this in the reverse direction. So here we say, in every zone, there live between 0 and infinity customers. So it can be an arbitrary non-negative number. But in every zone, we have between 0 and infinity many customers. And that is this asterisk symbol here is representing arbitrarily many, meaning infinity. Well, we have 2 more associations in this conceptual model. The first one, this one showing like a customer making an order or a customer ordering an order. Sounds strange, but let's keep it like it's written here. Yeah, so and again we can see these multiplicities that say that a customer orders between 1 and infinity many orders. Well, of course, a customer needs to make at least 1 order, otherwise the customer is not a customer. But a customer can make arbitrarily many orders. We can read it again in the reverse direction. Every order is ordered by, and now we have here precisely 1 customer. Every order is ordered by exactly one customer. Here we don't leave anything open, so 0 or more than one customers is not allowed. It has to be exactly one customer who makes an order. And finally, we have this association here to clarify like what has been ordered. And here I always say every order contains some menu items. And this sum is again clarified here, like how many menu items does an order contain? Well, every order contains at least one menu item because, well, otherwise there's nothing to order. And it can, however, contain infinitely many menu items. If we are giving a huge party and we have thousands of pizzas and pasta menus ordered, of course, this can get very big. We can read it again in the opposite direction. So any menu item or every menu item is contained in 0 until infinity many orders. Yeah, so every menu item is contained in an arbitrary number of orders. It can be the case that one item from our menu is never ordered. Maybe something like strawberry ice cream with tomato sauce. Yeah, that's never ordered now. Nobody likes that, so therefore we have this 0 here. But it can mean that some things like pizza fungi are really popular and they are ordered extremely often, so this number can be extremely large. And these things are all conceptually modeled here in this UML diagram. This is everything what I explained already. I should now mention that, well, these conceptual models, they allow more things to be expressed. And especially, so far I used only these black lines for associations. But there are special line symbols used in UML class diagrams, for example, to say that some of these associations can be navigated only in one direction. So if we have a shop object, we can see where this shop is located because each shop is located in some point object. So this is navigable in one direction. However, if we are given somehow a point with its x and y coordinates, we have no chance to find the corresponding shop in that point. At least it's not modeled here. So maybe we can compute that from the geometry to find out like which shop is located in this point, but it's not explicitly modeled. We cannot navigate from point to shop. Only if we are given the shop, then we can like access the corresponding point object. Then there's one special type of aggregation which simply occurs so often that it deserves its special symbol. And that is the aggregation, meaning just is part of. So it's a special association, meaning is part of. And well, we have maybe a wheel and a car, both modeled as a class. And now that we have an association connecting these two classes, saying that every wheel is part of 0 or 1 car. Well, of course, a wheel can also be part of a bicycle, maybe. Then it's not part of a car. But a wheel cannot belong to more than one car, at least not at the same time. And then we have a car which has 4 wheels as its parts. Maybe you can argue that there are cars already with 3 wheels, but then I would argue maybe that's not a car. It is something else. Let's give it a different name, maybe a 3-wheel vehicle or something like that. Yeah, so here, according to my model, every car has exactly 4 wheels. And, well, for sure, we could model that also. We could model that also like this. Car, wheel. Those are my 2 classes, and now I can use this association here, saying, okay, we have 1 here, or let's say we had 0.1 here, and here we have precisely 4. And now I use a standard association rather than this aggregation, and I write simply is part of. And that is exactly, it is precisely the same as expressed with this symbol. So there's no difference in these 2 models. It's simply in UML that these people who designed UML or who developed UML, they said such part of associations. This is part of relationships. They occur so often in our models that this deserves a special symbol, this diamond. And that you can see here on this slide. Okay, then there is furthermore this so-called composition. Okay, we have seen that aggregation means it's an is-part relationship, and the same applies to the composition. So also the composition means is part of. In the German universities, for example, we have faculties. We are a part of the agricultural faculty, and the agricultural faculty is part of the university. Well, in other countries, maybe that would be called a department of agriculture. Yeah? In Germany, it's called a faculty. So we are part of the agricultural faculty, and the agricultural faculty is part of the university. You can see also that every faculty is part of exactly one university, and each university consists of between 1 and arbitrarily many faculties. So what is the difference between the aggregation and composition? That is really not that obvious here, but the idea is simply that this university, well, that is actually necessary for the faculty to exist. So this part, the faculty, it cannot exist alone. The faculty needs a university, otherwise it cannot exist. So that is expressed with composition. In the case of the car with the wheel, that is different. A wheel can, of course, exist without the aggregate, the car. A wheel can exist even without the car, independent of the car, but a faculty never exists without a university. And that is therefore the composition. I think this distinction is maybe not too important, but in UML that's expressed with different symbols. Well, that was our conceptual model for the pizza delivery system. And we can maybe introduce these associations here as being navigable only in one direction. We could maybe also say that the order consists of multiple menu items, and on the other hand, that the menu item is part of an order. So this would be an example where probably we could have used also this aggregation relationship or this aggregation association type. That was our conceptual model, and this is actually a nice point now to end with this first lecture on the topic. We have seen how to develop a conceptual model for a pizza delivery service. It's probably not the most frequent application for us as geoinformation scientists, but it is, of course, a big business. It has become a big business in the previous, let's say, 10 years in Germany. You see these internet companies like, well, how are they called? Delivery Hero or Foodora or whatever. Yeah, you can see these bicyclists with these orange backpacks everywhere in Bonn. So such a company like Delivery Hero or Foodora or whoever, they of course would have very large databases like this about possible companies who could offer menus and the customers who need to register online and these things. So this is, when I designed this example, it was really meant as a toy example, and I had no idea that it could turn into such a big business as it is nowadays. So maybe this is even more interesting now than I intended it originally when I developed this as a toy example. What you will see in the next lecture is how to now go from the conceptual model to a logical model. And that means to go to a concrete implementation of our conceptual model. This can be done in different ways. Again, it depends on the application. What do you want? Maybe you want a database for persistent storage of information following this model. Then you need to implement this conceptual model in a relational database where this information is kept in a persistent manner. So you have tables representing your classes and all these things, and these tables are managed in a database system which can be accessed from maybe a client, and the database is run on a server or something like that. Or maybe you want a computer application, a program that you run, it reads some data, it organizes the data in an object-oriented model, it does some computation, and finally it terminates. So that would be an object-oriented Java program maybe. And also for such an application, this conceptual model would be equally valid and equally important. So we could also implement this conceptual model as a running Java program. And these two different ways, they will be sketched in the next lecture. But this is now a nice end for today. I hope you keep on watching these videos. Bye-bye.